Okay, let's dive into this explainer. We're going on a seriously fascinating journey today, tracking the evolution of artificial intelligence. We'll start way back with those early philosophical dreams of what artificial minds could actually be, and we'll follow that thread all the way to the modern breakthroughs, specifically the transformer architecture that are powering this massive AI boom we're literally living through right now. It all really starts with one fundamental question. Can machines think? Back in 1950, the brilliant mathematician Alan Turing posed this exact question. He basically planted a flag that established the stakes for the entire field of AI, way before the term was even widely used. But, Turing knew that arguing over a fuzzy definition of thinking was a trap. So, he brilliantly redefined the problem into something we could actually measure: the imitation game. It's a test where an interrogator tries to figure out who's human and who's the machine, just by typing back and forth. And what's absolutely incredible here is Turing's foresight. He argued that physical appearance, like, say, giving a robot artificial flesh, is totally irrelevant. It's the mind that matters, not the shell. And in that exact same 1950 paper, Turing had this amazing realization. He wrote, "Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's?" He was essentially envisioning a machine acting as a blank slate, one that learns through language, rewards, and punishments, rather than just being a rigidly programmed adult brain. This whole idea of a learning machine, it was decades ahead of its time. Section 1, the deep freeze, decades of AI winters. Let's look at how that initial soaring optimism violently crashed into severe technical and financial realities. Because realizing Turing's dream proved incredibly difficult. Early on, there was frankly massive hubris. Take the famous 1954 Georgetown IBM experiment. They claimed immense success in machine translation, and the media proclaimed a robot brain was translating Russian into English. But in reality, the machine only used a highly curated 250-word vocabulary on exactly 49 specific sentences. To put that into perspective for you, humans need about 8,000 words to just comprehend written texts. So, yeah, it was an illusion of progress. And this brilliantly illustrates the volatile cycle the field found itself in. Exaggerated hype would consistently lead to massive disappointment, which then triggered devastating funding cuts across the board. The 1966 ALPAC report completely crushed machine translation funding. In '73, the Lighthill report effectively dismantled AI research in the UK. By '74, DARPA had cut undirected funding entirely. And jumping to '87, the entire billion-dollar list machine market simply collapsed. These were the notorious AI winters. So the core reason for all these winters was something called the combinatorial explosion. Early rule-based systems were just incredibly brittle. Researchers vastly underestimated the sheer complexity of human language, things like word sense disambiguation, and the algorithms just ground to a halt on real-world problems. Why? Because they lacked basic common sense knowledge. They literally couldn't process exponential possibilities using those rigid, hard-coded rules. Section 2. The technical wall. Recurrent neural networks, or RNNs. The field finally thawed, but it wasn't long before it hit a brand new technical ceiling. Eventually, as computing power grew, the winters thawed. RNNs, along with more complex variants you might have heard of, like LSTMs, became the dominant architectures for natural language processing. Now, they work by processing sequential data step by step, maintaining a sort of memory of past inputs. And for a good while, they were absolutely the state of the art. But RNNs had a fatal flaw, and it becomes super clear when we compare them to what came next. Because RNNs process words sequentially, literally one by one, they are incredibly difficult to parallelize. That means you can't train them efficiently on massive data sets. Plus, they suffer from something called vanishing gradients on long texts. They basically forget information from earlier in a long sentence. Transformers, on the other hand, introduce parallel processing. This made them highly scalable and capable of instantly connecting distant context. Section 3, the breakthrough, the transformer architecture. This 2017 innovation was the definitive aha moment that shattered the sequential wall and sparked the current AI spring. So the crucial point is how this actually changes data comprehension. Think of it like this. An RNN is like having one single person read a massive document word by word. It's slow. And by the end, they've probably forgotten what was on page 1. A transformer, though, is like having an entire team of researchers reading the whole document simultaneously. Each person highlights the relationships between the words instantly, no matter how far apart they are in the text. It is a fundamental shift. The real magic behind this is a mechanism called self-attention. Basically, the model generates query, key, and value vectors for each word. It then calculates an attention score to determine exactly how relevant every single word is to every other word in the sequence. It really doesn't matter if a pronoun is 10 paragraphs away from its noun. Self-attention instantly grasps that distant context. It's like a giant puzzle coming together all at once. Let's move to and see how this builds into the full architecture. First up, the encoder takes the input and contextualizes the entire sequence at once. Second, that self-attention mechanism we just talked about scores the relationships across all the data simultaneously. Finally, the decoder uses that rich, highly contextualized map to generate the output sequence. The encoder and decoder are just working in perfect tandem here. Now, there is a catch. Since transformers process everything simultaneously, they inherently lose the concept of word order. I mean, the sentence, "the dog bit the man," looks exactly the same as "the man bit the dog" to a completely parallel processor. So to fix this, they use positional encoding. This injects mathematical patterns, specifically sine and cosine functions, right into the data. This way, the model perfectly remembers the exact sequence of the words, even while it's analyzing them all at once. Pretty clever, right? Section 4. The current AI spring. Let's look at how the transformer directly birthed the massive tools we use today. This incredible architectural shift really brings us to where we are today. The transformer is such a versatile engine that it actually powered the two most famous AI branches in entirely different ways. Google's BERT utilizes the encoder half of the transformer to understand context bidirectionally, so it's great at predicting masked words. On the flip side, OpenAI's GPT models use the decoder half to generate text autoregressively, basically predicting the next word in a sequence to create entirely new text. And, this architecture arrived right on top of some compounding victories throughout the 2010s and 2020s. We saw AlexNet have image recognition errors back in 2012, massive leaps in Google Translate, and DeepMind's AlphaZero and AlphaGo mastering the world's most complex board games. All of this culminated in the rise of large language models. And honestly, this powerfully validates Alan Turing's early theories about a child machine that learns from massive amounts of data rather than hard-coded rules. Now, what's really interesting about this is the staggering milestone of 100 million. That is the massive number of active users ChatGPT reached in just 2 months following its late 2022 release. I mean, it reinvigorated the global discussion on artificial intelligence practically overnight, pulling us definitively out of any lingering AI winter for good. The sheer scale of this current breakthrough is honestly hard to overstate. It's predicted that by the year 2025, AI investments by large tech companies will reach a monumental $364 billion. The entire industry has essentially reorganized itself around the massive potential unlocked by transformers and huge computational power. Which leaves us with a pretty profound question to end on. We've gone all the way from the rigid, brittle rules of the past to transformers dynamically powering models like GPT today. So has Alan Turing's imitation game finally been beaten? Have we truly achieved artificial intelligence? Or is history just waiting to repeat itself, and we're simply enjoying another very expensive AI summer? Think on that for a bit. Thanks so much for joining me on this explainer, and keep exploring.